research interests include molecular geometry and related applications. So today he's going to give us a talk with title Researches on Molecular Geometry and Related Application. So without further ado, let's please join me in and welcome Dr. Sheng. All right, you can get started.
Okay, good afternoon, everyone. Thank Professor for your invitation. I'm humorous to report our recent work today. My topic is researches on molecular geometry and relative applications. This is joint work with my supervisor, Professor Benzhou Lu, Dr. Minxin Cheng, and Ms. Zhaodi Cheng. I'm a PhD from the Institute of Computational Math and Scientific Engineering Computing, Academic of Mathematics and System Science, CAS. My talk is divided into 5 parts. In the first part, I will give the applications background about molecular geometry and introduce some definitions of molecular surface. Then I will talk about the motivation of researches on molecular surface construction. In the second part, it's about molecular sparse representation. Furthermore, the sparse representation method is applied to the image field. In the third part, we serving the continuous models by a pin. Okay. Biomolecules such as protein are the basic functional unities of life activities. Geometry modeling on the biomolecules is widely used in molecular visualization like this, and computer asset dragon design, and some biophysics and chemical information. Look like these movies. We use the FEM to simulation the ions the transform phenomena. We can the FEM applied to the Poisson-Boltzmann equation and the Poisson-Nernst-Planck equations by the molecular shape. So there are various kinds of the definitions for molecular surface, including the van der Waals surface, the solvent accessible surface, SAS, the solvent excluded surface, SES. These figures shows illustrations of VDW, SAS, and SES. Different from the previous definitions, the Gaussian molecular surface is defined as a level set of dimensional of the Gaussian kernel functionals. Well, this N is the number of the items, Xi and Ri are the location and the radius of item i's. The parameters D is positive and controls the decay speed of the kernel functions. C is the ISO values, and it controls the volume enclosed by the Gaussian surface. There are 2 parameters, D and C, can be chosen appropriately to make the Gaussian surface approximate to the SES, SAS, and the VDW surface field. Geometry modeling of biomolecules plays an important role in various applications. New challenges arise in simulations in variety extremely large biomolecular complexities. The computational cost for biomolecular surface constructions increases as the item number becomes progressively larger. So we propose the molecular sparse representation method. Okay. First, let's review some preliminary knowledge. The volumetry electric density maps are often modeled as the Gaussian density maps. The definitions of the Gaussian density maps is as follows. This. Where the parameter D is positive and controls the decay rate of the kernel functionals. Xi and I are the location and the radius of atom I. The Gaussian surface is defined as a level set from volumetry electrons density maps, where the C is the ISO values, and it controls the volume equals by the Gaussian density maps. Okay. The radial basis function is written as this Xi, where Xi is a negative functional. Ci is the center location of the iron's basis function. RBF has basic properties as follows. As we all know, the typical truth of RBF is the Gaussian function. So the level set of the Gaussian RBF is standardable sphere equations. Based on this point, we can modify the standard sphere equations to the free ellipsoid equations. Compared with the RBF, we put forward the ellipsoid RBF with the parameters with respect to the location sizes and strips. The ellipsoid Gaussian RBF can be written as this precise, where the C is the center of the ellipsoid Gaussian RBF. D is a diagonal matrix, where the Di defines the length of the ellipsoid along the three main axes. Theta is the total rotational matrix, and it is equal to the product of rotational matrix from the three directions. Okay, the RBF neural network is a special FN consisting of the three layers. It contains an input layer, a hidden layer for nonlinear exponential functions, and linear output layers. The ellipsoid Gaussian RBF neural network psi is as follows, where the Ci is the iron's ellipsoid RBF centers of the hidden layers. Di represents the length of the corresponding ellipsoid RBF around the three main axes of the hidden layers. Theta I is a rotational matrix of the iron's neural. Wi is the output weight between the iron's hidden neurals and the output node. Last year, we proposed the molecular sparse representation method, and this work is published in Journal of Chemical Information and Modeling. So I will introduce our models. The main group of this study is to create a sparse representation of the Gaussian molecular model by the ellipsoid RBF neural network, according to the definitions of volumetry density maps and the structure of the ellipsoid RBF neural network. The lost functions for sparsely representing a Gaussian molecular models is as follows. This, and the corresponding constrained coincidence is W and DIP. The first term of our models is density error between the sparsely represented molecular and the original molecular at the training training points set xm. And the second time EL is a L1 recognition team to reduce the both network complexity and overfitting. The formulate is as follows EL1. And the X is the network parameters. The two parameters ES and EL are used to balance the two target accuracy and sparsity, and the constrained conditions are expanded as follows. One, the first constrained conditions indicate that the corresponding ellipsoid Gaussian RBF is non-negative. Two, the second constraint conditions implies that the exponential functions do not blow up at infinity, which is consistent with the fitting functional phi. Okay. In these slides, we describe the algorithm to construct a sparse representation of Gaussian molecular density by the ellipsoid RBF neural network. The inputs of our method are PQL files, which include a list of centers and radius of items. The output of our method is network parameters, which contain the centers, the length, the rotation angles of the ellipsoid RBF neural network, and the weights connecting the hidden neurons to the output layer. The algorithm outline is as follows. First, we set the training points xm and the label corresponding value phi xm. Secondly, we initialize the ellipsoid RBF network. Third, we optimize the loss functions using the ADAM algorithm to minimize the sparsity and the error terms. Alternatively, these figures illustrates the process of our algorithm. The result shows that use our method, the original Gaussian surface is approximated well by a dimensional of match field ellipsoid Gaussian RBF. In order to train a network, in the first step, the training point set is initialized. The molecule is put in a bounding box omega. The bounding box omega is described into a set of uniform grades as shown in middle figure. The training data are the grade points. In this slide, we initialize the ellipsoid RBF neural network parameters. Considering that the Gaussian RBF is the degradation case of the ellipsoid Gaussian RBF, the activation function psi can be initialized in the same manner as phi. That's the strategies of initialization as follows. Number one, the length of the ellipsoid RBF D are set to be as constant vectors. And the initial angles of the ellipsoid RBF theta are set to be zeros.
Can I ask you a question? What is the value of n? How many ellipsoids you use typically?
It include all number of the item. If the molecule have 100 items, the initial ellipsoid ellipsoid Gaussian RBF, the number of ellipsoid Gaussian RBF is equal to the number of the atoms.
But what's the largest n that you ever use in your thesis? 100 or 1,000 or how many? The largest you ever use?
It's case by case.
Tell me the largest that you use in your thesis.
Professor, once again.
Minlan, can you ask him the question? What's the largest number of atoms that he used? How many ellipsoids did he ever use? The RBF, basically the basis, the size of the basis.
Can I speak Chinese to him?
Okay.
Yeah.
OK， 老板在问你，就是你个 n 最大的设成多少？你最大的 network 里边，你 n 设成。
这个得看分子，就是如果这个分子。
他问你最大的是多少，在你的 thesis 里边，最大的用过多少
？8,218.
Okay. Thank you.
Okay. Also, I have a quick question. So, what's the type of your, like, is there any special constraint on the type of atoms that you're simulating, or it could be any atoms? Do I need to repeat the question again?
你讲一下中文吧。
No, I mean, 就是你对这个 atom 的种类有要求吗？
没有。
OK.
It means no. I understand that it doesn't matter, right, Minlan?
Yeah.
Okay. Okay. Please proceed. Yeah, please continue.
The initial centers coordinate C of the ellipsoid RBFs can be given by the centers of the items as follows. While the D, C, and theta has been chosen and the item radius are given to initialize the ellipsoid RBF activation functional precise similarly to the RBF way. We set the weight W of the ellipsoid Gaussian RBF is as follows this. Okay. After initialization of the ellipsoid RBF neural network, the sparsity of Gaussian RBF representation is computed by minimization the loss function. We aimed at finding a sparse vector, weight vector, and a sparse decay rate vector of the psi, such that the ellipsoid RBF neural network psi is a good fit of phi at the training point set. Algorithm 1 represents the main modules of our sparse optimization method, which is described below. The main process is module 6. So I will introduce the chat flow of step 6. Step 6 shows the numerical algorithm of optimization for the lost functions. Step 6.1 shows the ellipsoid RBF neurons useless if the corresponding vector Wi connecting the unhanded neural to the output layers is less than the tolerance period check steps. In this work, we set the tolerance 1 equal to 10 to the power -3, and the check step equal to the 20. Step 6.2 calculate the prediction value psi for all the training data point set. Step 6.3 checks the maximal of error between the psi and phi at the training point data set and update the coefficients row 1 and row 2. Step 6.4 after the performing the sparse iterations, which the number of the effective neurons fixed it, keeps performing some steps of the minimization of the ES to achieve the better accuracy of the approximation on the training points data. Step 6.5 updates the network parameters and optimize the loss function by the batch item method. Okay, this movie shows the optimization process, and this figure shows the loss function and the number of ellipsoid RBF neurons decreases as the number of the iterations increases in the sparse optimization produced for the molecular ADP. In this experiment, the max iterations and the sparse iterations are set to be the 10,000s and the 6,000s respectively. After the 6 iterations, row 1 is set at 0 to minimize the ES time slowly. So the value of the loss function has a absolute change. The number of the ellipsoid RBF neurons decreases dramatically during the iteration process. As shown in these figures, the model with the 6 ellipsoid RBF neurons achieves minimal error with a relatively less number of the ellipsoid neurons. Okay, the 20 biomolecules are chosen to be sparsely represented by our ellipsoid RBF neural network and the sparse RBF method. This table shows the financial number of effective basis functions from the results of our method and the sparse RBF method. In this figure, the change of the sparse reduced with respect to number of items for different descent rate. D equals to the 0.3, 0.5, and 0.7, as shown by a Solon lens with a square, triangle, and circle markers. The results show that the largest the decay rate D, leading to the more rigid and complex molecular surface. The bigger the sparse radius is going to be. The sparse radius for the Gaussian molecular density map with the D equal to 0.3 are smaller than those of Gaussian molecular density map with D equal to 0.7, as shown in this figure. This table shows the sparse radius for 20 test proteins. The maximum sparse radius is 0.1419. The minimal sparse radius is 0.0421. Okay, the figure shows some visual results of the sparse optimization model. The first claim shows the original Gaussian surface for four molecules. The second column is the financial ellipsoid Gaussian surface in our method, while the blue points respect the location of Gaussian RBF centers. It indicates that our method needs few number of the ellipsoid RBF neurons to respect a molecular surface. The third column is the original surface overlapping it with the financial surface. It shows that the financial surface is close to the original surface. The last column shows the configurationals of the ellipsoid RBF neurons in a sparse representation of four molecules from our method. It dimensionals that after the process of sparse representation, the number of ellipsoid RBF neurons are much sparser than the RBFs. Obviously, each ellipsoid RBF is a local shape that corresponds of the molecular shape. In these slides, we first check whether the Gaussian surface is provided after the process of sparse representation through our method. The area, the volume enclosed by the surface, and the Hausdorff distance are the three criteria to judge whether two surfaces are close enough. The criteria can be calculated on the triangle mesh of the surface. The triangle meshes of the molecular surface before and after sparse representation are generated through the matching cube algorithm. For the triangle surface mesh, the surface area S is determined using the following equations. The volume V enclosed by the surface mesh is determined using the following equation. And the Hausdorff distance between the two surface meshes is defined as follows. In our work, we use the software material to complete the Hausdorff distance. The areas and the volume enclosed by the surface before and after the sparse representation for each of the molecules are listed in this table. The Hausdorff distance between the original surface and the financial surface for the biomolecules are also listed in the last column of this table. The relative arrow of the area is about 10 to the power minus 2. The relative arrow of the volume is about 10 to the power minus 3. The reactive arrow of the Hausdorff distance is about 10 to the power minus 1. So this result shows the financial surface is close to the original surface. Oh, okay. We here also tested the applicable of the original and the sparse surface in a computation of Poisson-Boltzmann equations. The boundary element method, the software used is a publicly available PB solver, AFMPB. This table shows that AFMPB can undergo and produce the convex results using the sparse represented surface, and the calculate servant energies are close to the results using the original surface. This figure shows the computed electrostatic potentials mapped on the molecular surface. In the future, we can consider adding the charge information to the sparse representation. Furthermore, the sparse representation method is applied to the imagery fields. Similarly to the previous method, we present a model and a corresponding algorithm for sparse representing of imagery data. We use a RBF neural network with a small number of the ellipse Gaussian functions to approximate the input images. The sparsity of the imagery data is attributed by solving a nonlinear optimization problem with the L1 regularization in our models. The cost function in our sparse ellipse RBF, the neural network for representing the imagery sparsely is as follows. The left terms is the mean squared error between the tilde psi and psi at input points xi. Psi is the input imagery, namely the label of our model, and the tilde psi is output the sparse ellipse RBF neural network. The right terms is also the L1 regularization. Xi is the xi is the location of the nth pixel. Cj is the centers of the J's active function. Okay. Then we will modeling variable initialization. We take the image pixel coordinate at the corresponding pixels as the inputs and the corresponding label in our models, make them as the x plus x respectively. And the P is defined as follows. Since the general RBF neural network is the declination case of the ellipse RBF neural network without lose the generality, the initial DJ is set as a consistence vector. Similarly, let the initial theta be zeros. In this work, we set the initial centers to the pixel coordinate, namely Ci equal to Xi. After choosing the DC theta, the weight vector W is set as the previous method. Okay, to present the sparse level for imagery representation, we defined the sparse radius SR as this. And we make the comparisons between our method and the KSVD method. In our experimentals, we use the PSNR as the objective evolution standard for imagery reconstruction quality, and it defines as this. To verify the effectiveness of method in BSDS 500, we present the three reconstructed image of BSDS 500 using the two methods. We select the four images of the size 28 times the 128. For experimentals, the three tables respectively show the PSNR of the reconstructed in images at SR equal to 0.01, 0.015, 0.02 using our method and the KSVD method. The three tables and the corresponding figures show that our method is better than the KSVD method, and our method have more sparse result. Look these figures. The first column shows the four original images. The second column is the corresponding Gary scale images. The third column is the sparse representation result by the KSVD method. And the last column shows the sparse representation results using our method. It dimensionals that after the process of sparse representation, the number of the ellipse RBF neurons are much sparsely than the original image pixel. Obviously, each ellipsal RBF is a locate shape described of the image. Okay. The last work we solved the continuous models by using the physics informed neural network. And our work is based on the following papers. Okay. First, let's review the preliminary knowledge nodes. The deep network structures and property here is similar to the resonate, which is built by the static several residual block. Each the residual block contains the one put, two weight layers and two nonlinear transformation operations with a scale identity connecting and one output. Robed are the activation functionals used in the current work. And the theta is the full set of the all weight and the bells the parameters in the neural network. Okay. The loss function of Poisson-Boltzmann equations is as follows. So we use the Monte Carlo method to calculate the integrate. We also consider the steady state Poisson non-Planck equations. Similarly, provides the method. The loss function of Poisson equations is as follows. And the loss functions of the non-Planck equations is as follows. Okay, the total loss function equal to the dimensional of the loss function of Poisson equations or the loss function of non-Planck equations. Consider the following the Poisson-Boltzmann equations with the Newman boundary conditions. The analytical solutions is as follows. For notational convenience, the variable p represented this. The loss functions is as follows. We melted the p by the xi times 1 minus xi to satisfy the Newman boundary conditions automatically. This table shows this method, the result of this method. The relative L2 errors is about the 10 to the power minus 3. The relative H1 errors is about 10 to the power minus 3. Okay, we consider the steady state PMP equations with a small solutions as follows. Here the computational dynamic domain omega is the cubers in two dimensional. The boundary condition and the left hand side functionals are chosen so that the exact solutions is given by this. Consider the Dirichlet boundary conditions in two-dimensional. Relativity L2 arrows are recorded in the first table in the first table for different mini batch size in the domain with fixed mini batch size on the boundary, and in the second table for different mini batch size on boundary and the fixed mini batch size in the domain, respectively. From these results, one can expect that a balance of simply points in the domain and on the boundary will yield the optimizations accuracy. Consider the Dirichlet boundary conditions in two-dimensional. This table recovers the relative L2 arrows in terms of the several activation functions. From this table, it is recognized the choice of activation functions is quite important. The field of ReLU is due to the low regularity of the activation functions and the use of the higher derivatives in the loss function. Also consider the Dirichlet boundary condition in two dimensions. Table record the relative L2 arrows in terms of the neural depths and the neural width m, respectively. It is expected that the approximational arrows reduce as n and m increase to some extent. Also consider the Dirichlet boundary condition in two dimensionals. The relative L2 arrows is recorded in this table for different penalty parameters. In the theorem, the damping parameters lambda should be in infinity if the exact solution is found. In practice, instead, for a given DNN, lambda should always be a finite number. It is observed from the table that the larger the training parameters lambda is, the better the approximation is. In this example, we consider the three-dimensional PMP equations. The exact solutions is as follows. In these examples, we can modify the parameters C bar, V app, L to adjust the conventional strength and the boundary condition. The C bar can influence the ions concentration. The V app implies the electric field, and the L is the size of the domain. Obviously, if the C bar, V app, and the L are large, then the convector string will be large. Okay. Conventional neural methods such as the FEM often lead to the divergence and or abnormal neural results while dealing with the continuous models. This result shows our method can approximate the solution of the models well and is not sensitive to the convention dominated the problems in PMP models. Okay, finally, let's summarize this topic. Firstly, we have developed the ellipsoid radio basis function neural network and the algorithm for sparsely representing the molecular shape. The machine learning model will train it by the optimizing or nonlinear loss functions with the L1 localization. Experimental results reveals that our algorithm can represent the original molecular shape with a relative highest accuracy and the field scale of the ellipsoid radio basis function neural network. Furthermore, the sparse representation method is applied to the image field for the completed image data. The ellipse Gaussian radio basis function neural network with the sparse optimization technical is used to represent the imagery sparsely. The experimental results shows that our method can represent the input imagery with field ellipsoid Gaussian functions, and the accuracy is high. Finally, we solved the continual models by the use of physics-informed neural network. The result shows that the method can approximate the solution of the models well, and it's not sensitive to the conventional geometric programmed in PMP model. Okay, this is a list of my publications. Okay, thank you for your attention.
Thank you, Sheng.
Thank you, Professor.
Why did you switch to, if RBF seemed to work, why did you switch to pins? Did you understand my question? The RBF method, the RBF neural network, worked well.
Oh, okay.
Why then you change to PIN? PIN.
Because the RBF neural network is sensitive to the dimensionals.
I see.
So we use the pin.
Okay. So for scalability, I see.
Okay.
John Hoon, do you have questions? You have a question?
Yes, I have a question. I think I missed the first part of this research talk. Yeah, it was interesting talk for me, but I wanted to understand the background of the problem. So the problem is it looks like a molecular geometry modeling. So why is it problem? Because this application is also going to be able to our application, because I am working with some similar radio basis network basis networks approach. So I understand the problem. So would you be more clarified?
Sheng, maybe go back to your slides, the beginning of the slides, to show the setup, the formulation of the problem. Minlan, can you help?
你能把你的 slides 调到你的最开始的那几张？
OK。
你在调吗？
哎，
你的屏幕好像哦 ，OK， 下一页，background。
So what is the psi? Is it probability density or state function? So I saw
This one, yeah.
yes. So what is the psi?
What does psi represent? I think that's the question. Physically, what does psi represent? Minlan.
就是你这个 psi 你有的物理含义是？
The level set of the psi is a ellipsoid equations.
I mean the physical quantity. So is it a probability density or state function, or so what are the measurements for psi?
就是你这个 psi 是probability density 还是有什么其他的物理含义吗？除了这个？
这个我不知道，这个我没有考虑过。
You can speak Chinese. You can speak English.
I haven't considered this physics.
Okay.
Anybody knows? Anybody from the audience knows what psi would be? Probability distribution sounds like reasonable. Level sets of that.
Maybe let me ask him again. 是，就是你那个 psi 就是个啥？这是啥？就是这个字母代表什么意思？就是
这个 psi 就是 indicate 的 ellipsoid 的高性 RBF。
OK， 就是
It's a basis. It's a basis only.
OK.
But go back. Can you go from the beginning? When you have the expansion in terms of he has an expansion. Zhonghong, he has an expansion. No,
就是在那个展开的时候，就
go
那个
forward.
expansion。
There's an expansion somewhere. Next one. Next. Oh, here. He's got look. He's got the yeah. So electron density map. Yeah. For example, it could be like that for. Yeah. I think this picture is. Then go to the next slide. Next one. There's one expansion in terms of next one. Here. So, okay. So here's the capital psi. He writes in terms of this basis. R cube Some sort of geometry representation, but that represents maybe charge density or something like that, the atomic structure. But
yeah, I think I can now understand. Yeah, it is the electron density map. So my next question is about the property of the density map. So is it a dynamic, or so are you interested in understanding the dynamics of the molecular geometry? Just a static problem. Is the problem just a static or dynamic?
is there time? Is there evolution? These atom configurations, are they evolving? Are there interactions which there's transient dynamics? I think there's not. It's just a representation here. They try and, but yes, that's like in proteins. When you do proteins, that's a big issue, right? The static problem, or the dynamic. I don't think there is a dynamic here.
Okay.
I think, John, my understanding was that they use this RBF to sparsify the representation. It's a very complex surface. That's why they show also the imaging data. And they try to see how much they can sparsify the basis. Because remember, he had the plot where he had the number of atoms, right, which was the green curve. And then he had different degrees of sparsification. So although he was saying that one ellipsoid represents a neural network, actually they're trying to sparsify that. So they were like an order of magnitude less number of ellipsoids than atoms. Sheng, can you go forward go forward, please? In your results, in this section, the results, here. Yeah, you see this plot? So there's no dynamics. There's nothing is moving. It's just a sparse. You see here the green curve, right? That's the number of atoms.
Okay.
So if you look at that, the blue curve is already an order of magnitude less ellipsoids, and then they have this parameter D that they change, and they can go down even almost 2 orders of magnitude, not exactly, less than the number of atoms. So it's a so that's like one snapshot. You freeze the molecular structure, one snapshot, and I think that's it.
Okay, thank you.
Well, that's an interesting problem to actually know how to, in time, advance this. You know, if you have an equation, and that's. I'm talking to Lulu and some other people about this because that's what I'm interested in right now. But that's so easy. I think Minlang, I think it's difficult to communicate, but Sheng Gui, xie.
Thank you. Thank you, Professor.
All right. Bye, everyone.
All right, that's the end of today's seminar. Everybody take care and have a good weekend. Bye.